Welcome, everybody. Good afternoon. On behalf of Viavi Solutions, I want to welcome you to our webinar today. My name is Gloria Warland. I'm in the marketing group, and I work with the smart people in our company from our product management group and our solution experts. This is our third and final session in our Managing Uplink Interference Best Practices series. Our topic today is on external interference. Before I introduce our speakers, I want to let you know that this session is being recorded and it will be added to our website in a few days as an on-demand and available to listen to it again or to share with colleagues who weren't able to join us. All lines are muted, but we are monitoring the Q&A. And so throughout the session, so if you have questions, that little button is at the bottom of your screen. Please feel free to send questions to us or requests as we're going through the session. As I mentioned, it is being monitored and we'll try to be very responsive or at least direct you to when we'll cover that information in the presentation. I'm pleased to introduce our speakers today. We have Eduardo Inzunza, who is with our product management group, and we have Dan Smeja, solutions domain expert. Right now, I know you're ready to hear from them, so I'm going to turn it over to you, Eduardo. Thank you.
Thank you, Gloria, and hello, everyone. So we're going to be talking again about uplink interference, and in this case, it's going to be about external interference, as Gloria mentioned. So the things that we want to cover, and by the way, throughout this presentation, we're going to be giving some demos, as well as probably going to be pausing in a couple of times. So you can send your questions in and we'll try to answer them. So the things that we want to learn from today's webinar is to understand what are external interference and in which process we can find them. These external interferences are now becoming a little bit more challenging with 5G TV carriers. And that is typically the case for any carrier that is being transmitted above 3 gigahertz. And that happens to be the case of mid-band or C-band. So we're going to try to understand what's going to be the best way to test those. And we're going to be giving you a demo about TV autogated spectrum capability. Next, we're going to be trying to understand the different types of interferences, as well as how we're going to be able to assess for intermittent interferences. And that it's going to involve a little bit of a post-processing analysis. So we're going to be going through an example as well. And once we have found that interference profile, then the next step will be how we can locate the source of that interference. And we're going to be giving you a quick demo about interference hunting solution that is called Interference Advisor. And we're going to be closing with some references. Okay, so let's get started. In this series, we have presented first on how to do PIM detection and make a distinction between external and internal PIM. The next session that we did was about synchronization between the network or inside of the network between two cell sites. And that happens to be due to improper sync and timing between two cells. So we cover that and what was the best way to analyze the sync and timing of a cell site. And today's session then is going to be the final, which basically covers on in which way we can validate and mitigate external interferences. Okay, so interference, as we know, affects the uplink. And that happens because when the downlink is transmitting signal, let's make the assumption that typically the radio is transmitting, say, a 43 dBm power, and it has a sensitivity of about, it depends, and I think you might remember all the different sensitivity levels that we presented in a matrix when we talk about PIM. So in this case, let's make the assumption that the radio has a received sensitivity of neg 101.5 dBm. Okay, now on the other side, we have the mobile phone, a UE, that transmits power of about 23 dBm. Notice the big difference on transmission power, and the resistance sensitivity, it's about -87.5 dBm. So the problem with interference in the uplink is because when we have an interferer that is close to the UE, that it's going to affect the uplink because the transmission power of the uplink is not strong enough or not as strong as the downlink. So therefore, it's going to be competing with interferer. So that is the problem. Now, what kind of devices can cause these type of uplink interferences? And I'm referring to external devices. There are multiple of them. Here are just a few examples. We've seen a lot of broadband amplifiers that they sometimes go off frequency and happens to land in the carrier's frequency. Video cameras have kind of sometimes that behavior. Welding machines, and that it's kind of an interesting type of interference because when that happens, we've seen that it's an interference that is not constant. It all depends on when the machinery is active and is doing its job. That's when the interference occurs. So it's intermittent. And the other characteristic that we have seen is that it's frequency hopping. So meaning that doesn't stay at a specific frequency, but moves in time across different frequency steps. So we're going to be talking about that and what's going to be the best way to analyze intermittent and frequency hopping interferences. Anyway, some of the other sources of interference, smart grids that sometimes they go off. Even sometimes everything is not being active. However, the oscillator just goes crazy and sends out a tone that again happens to land into the uplink of the carrier. Billboards, or even leakage on cables, that cables are just left open. So anyway, these are just some examples of potential external interferer sources. Right. So what's the process that we typically follow for an external interference? We receive a key performance indicator or a statistic or a metric from the management system. Then we try to assess the interference, and that is by characterizing that interference. And by that characterization, I mean how that interference behaves. What's the power level of interference? How is it intermittent or is constant? And what type of interference it's in the sense of it's just a narrow band, it's a wide band, it's frequency hopping. So that's the first step typically that we do to assess for the interference profile. Next is, okay, so now that we understand how the interference behaves, then we're going to be looking for the location of that interference. So we have a methodology that we can automate that process of interference finding. Once we assess the area that the interference is coming from, then we just do a walk test with persistence spectrum or with a radar chart or different type of methodologies using a directional antenna to find that source of interference. Can be, for example, in a building, so we need to do a little bit of walking between different floors, if you will, to find that cause of interference. And then at the end, we certainly can report what that interference source was. Okay, so now I'm going to be shifting gears, but before that, that was just the general introduction about external interference. I'm just going to pause for a second just to see if there are any questions so far.
Eduardo, the only question we have came in right before the webinar started, asking to discuss PRBs in depth. Wow.
Okay.
That was a slip. I'm going to recommend we focus on Uplink. PRBs, obviously for this one, not so much the downlink because they changed drastically. So at some point, if we can touch on that, that would be great.
Okay, we'll
Thank you.
do that.
Thank you, Robert.
Okay, so now let me just talk about external interferences in TDD carriers. So as I mentioned before, anything that it's above 3 gigahertz is time division duplex. And once again, that means that the uplink and downlink are being transmitted at the same frequency, but at different time slots. So it's TDD based. Here's just a kind of a graphic of, okay, we're sitting on a specific frequency. This just happens to be a CBRS frequency. And as you can see through time, we see a period of time or number of slots. In the case of 5G, number of symbols that the downlink is being transmitted. Then it gets quiet, it exists a guard band period, and then the uplink starts talking, and then the downlink, and so on and so forth. This configuration, and I think we discussed this before, but this configuration is being defined by 3GPP with different slot formats. So this is just an example of the different slots that exist, or it has been defined, as I mentioned, by 3GPP. We have up to 56 different configurations on how these downlink, uplink, and flexible slots can be allocated, can be used by a carrier. Okay, so I'm gonna, typically for TDD signals, we used to have a methodology called a gated spectrum. So by gated spectrum, we were able to assess the signal on both domains, time and frequency domain. So first, here we have the time domain on top. And actually, let me just try to highlight. So here's, as you can see, my time domain view. And this happens to be 10 milliseconds. So this is a LTE TDD signal. And as you can see, we have a good distinction between the active slots and the slots that are quiet. This is because all these are downlink, uplink, downlink, uplink, and so on. LTE, the way in which those slots were assigned between downlink and uplink is based on a subframe, or every 1 millisecond you can make that transition. So here we have a couple of gates. As you can see, those are the ones that are highlighted here in blue. And those are the gates in which the spectrum is going to be triggering. So down below here, we have the frequency or the spectrum view, if you will. And this spectrum, again, it's going to be based on the timing that we have allocated for the uplink. So as you can see, we have a couple of gates, so that increases the probability of intercept for interferences. And clearly, we can see now the interference. Okay, that works very well. But what happens with 5G? With 5G, the time that the uplink can be allocated is not longer 1 millisecond or one subframe, but it's much narrower. How much narrower? This is a little busy slide. We talked about it in a previous webinar, but let me just go through it quickly. Now I've tried to answer that PRB question. So here we have the carrier, any kind of bandwidth. This is frequency, we have power, this is my carrier, we have multiple resource blocks here being transmitted out. So resource block of PRB is right here. And then from a time domain perspective, so here's one frame, we have again power, and here we have time that is divided by different subframes. And based upon of the numerology is the difference of carrier spacings, or the width of these subcarriers is basically how many slots I'm going to have in my frame. For example, LTE 15 kilohertz, 5G numerology 0 also is 15 kilohertz. So here we have 10 slots, and as you can see, it's about 71 microseconds per slot. Now, if we are in C-band, for example, the numerology being used is 30 kilohertz. So that therefore I have now 2 different slots per subframe. So that goes down to 35 microseconds. Now, if I analyze or I look into each of those slots, I have different symbols. How many? I have 14 symbols. So on the first one, for example, it's 0. So in this 0, I'm going to explode, if you will, all the symbols within that slot. And as you can see, this configuration is 0, meaning that all of the symbols are downlink, and so on and so forth. So we have a sequence here, but then I have a transition. Now my slot is configuration 44. And as you can see, I have a number of symbols, 6 of them being downlink. And then I have a number of them, 5 of them being flexible, and then uplink. And then the rest of them is 1. So as you can see, the time allocated for downlink, flexible, and uplink, it's much narrower. So that creates a little bit of a challenge when we want to assign a gated sweep spectrum to analyze for the uplink. Now, the other comment that I want to make is that these flexible slots also is giving us an opportunity, because as you can see, this is the guard band or the guard period between downlink and uplink. And in this example, I have all these 6 different symbols that nothing is being transmitted. So if there's, well, nothing from the network is being transmitted. The radio is not transmitting at this time, nor the UEs. So if we have an external interference transmitting, this is going to be my ideal time that I can assess for that external interference. Why? Because then I'm not going to have any signal from the radio as downlink, nor any signal from the UE as uplink. So everything should be clean during this period of time. And again, making the assumption that everything is properly synchronized. So how does that look from a frame perspective? So here I have my frame. Again, this is the case of 30 kilohertz. I have my 20 slots being distributed. And as you can see, I have my downlink section, my flexible. And as you can see, here's that transition between downlink and flexible. And then I have my uplink and so on and so forth. Okay, now let me just close this out with a PRV. So a PRV is this power of resource block that we have a number of subcarriers. How many subcarriers? 12 subcarriers. And how many symbols? 14. So a PRV is basically that minimum unit of resource elements, and that those resource elements are basically this matrix, if you will, of a number of subcarriers by number of symbols. So in this case, I have 12, and then I have these 14 symbols now that constitutes or forms a PRV. Okay, let me, well, actually, before I continue, let me just, again, stop for a second, probably a little too much information, but really wanted to explain how for 5G TDD is a little bit more complex. At the same time, we have some opportunity here if we have the ability to tune our analysis into the flexible slots in an easy way. We can find external interferences very, very easy. So let me just pause and see if there are any questions.
No questions pertaining to this. Couple comments from Alexander. I'll look into that. Some potential confusion between slots and symbol in some of our diagrams, but I'll look into that with you after the webinar. So good catch if we see it. Yeah, this is a tough one, Eduardo. I say we move on, get to the fun stuff.
Sounds good. Okay,
Yeah.
so as I mentioned, what's going to be the best way to find those flexible slots or flexible symbols, to be more precise, automatically? So actually, we have implemented that capability. So this is an example where we just find our 5G TV carrier. We automatically find our pilot signal or our SSB or beam. And then once we do that, we just can go into obtaining our downlink control information. Or basically what that means is we're going to be able to obtain the distribution of all those different slots and symbols between downlink, flexible, and uplink. And then with this information, now that we know where are those slots, basically we're going to have a visibility of my frame, and then we can also zoom in into my flexible slot. And as you can see here, I have visibility of all the different symbols, my 14 symbols. And then here is where I'm going to be triggering my persistent spectrum. So as you can see here now, we have now a persistent spectrum. And in this specific case, is as narrow as 71 microseconds. So it's very small. And that, again, thanks to our ability to look for the flexible slots and then analyze the signal. So with that, let me just actually, we can do a quick demo. Here I have my unit. Let me just shift my display here. So bear with me, just give me a second.
So Eduardo, as you're tuning, I'll answer the question. What tools are we using to tune out the flexible time slot? So the product that we're discussing is the Viavi One Advisor 800, where we have GPS attached, obviously either a directional and or omni antenna, and we are able to demodulate, do some signal analysis, if you will, and get to the time slot allocation. So we're using our tool, which is set up to automatically understand the frame structure. Hopefully that helps.
Thank you, Dan. So here, basically, that solution that Dan just described via One Advisor, I'm just remoting into this unit here in my house. I just did a blind scan between 3.7 to 3.9. I found this carrier happens to be a 40 megahertz signal. Actually, it's coming from AT&T. But once I have these, I can just look into the spectrum. I just want to take a look at the behavior and the power level of this carrier. And there it is. So I have my signal. He's not too strong. It's a little weak, but that's probably okay to do the analysis. And the analysis, I just have selected the TV autogated spectrum. And as I mentioned, I just went through the process, found the beam, and also found the frame configuration. And here, as you can see, I'm just triggering on those flexible slots. So here I have my persistent spectrum only looking for those flexible symbols. And here I have my waterfall. Now, how does that look? So I'm just gonna show, I'm just gonna go into my auto configuration. This is where I basically found the signal and the beam. So roughly, this is how it looks from, this is what I briefly explained on my frame with my 20 slots. And as you can see here, this is what I've obtained automatically. The distribution of my frame or the configuration of my frame between downlink, up, flexible, and uplink, and so on. So once I have this information, as you can see, I have selected my slot number 3, and then I just move to the next view. And this next view is within my slot number 3. And as you can see here, I have my downlink, the transition, and then the transition being my flexible slots, sorry, my flexible symbols, and then my uplink. And then as you can see here, I just configure my spectrum to be triggering in these 2 symbols, 7 and 8, and that's basically what I'm seeing right here. So pretty simple, straightforward, and again, we're just taking a little bit of advantage of the intelligence that we get from the network to obtain the frame configuration and do it automatically to assess for any external interference. Okay, let me move back to the presentation.
So while you're doing that, we had a couple questions come in that we've answered, but Randy just asked one, why we would want to measure the flexible slot versus the uplink slot. It's a great question, Randy. Traditional gated sweep measurements for uplink, absolutely, we're looking at the uplink time slot. The drawback of that is the phones near you, whether they're in your car with you if you're driving, or the customers around you as you're moving, are also using that uplink, and so they will affect the measurement accuracy. Obviously, the flexible time slot, as Eduardo showed in a previous slide, is this transition gap between uplink and downlink, and there will be no traffic there, no uplink, no downlink. So when interference is found in that flexible slot, it is absolutely an interferer. It's not a mobile phone that's we're picking up from the spectrum analyzer. It's not the downlink. It's that gray area in between, and it's why we like to talk about it. It's a new feature that we've I hate to use the word discovered, but that's the word I'm going to use. Using uplink is absolutely valid. You just have to contend with the same problem you have in FDD uplink interference. You have mobile phones that are stepping on your spectrum. So that's why we talk about this. It's a new way to do it, specifically in the TDD format. Go ahead, Eduardo, after you.
Thank you, Dan. Okay, so now I'm going to be shifting gears, and I'm going to be talking about roughly how we group the external interferences. And by that, I'm just getting into the profile or the characterization of external interferences. So typically, we group them in three categories. The first one, it's a wideband external interference. So it's there, it's in the close to the noise level, but it's a wideband signal. And typically for that, we do a test by the whole band. We refer that as a channel power. So anything that is above 2 megahertz, typically that's a wideband interferer. Some broadband amplifiers, some of those type of devices generate this type of interference. Next one is narrowband interference. We just look into one specific frequency, and we just look for the strength of that frequency. We just refer that as RSSI, or received signal strength indicator. So this is, again, very narrow type of signals that are there and are not moving in frequency. And the third one is basically something that is narrow, but it's moving on frequency. And as I referred to that example of a welding machinery, that it's a narrow frequency, but it's changing. It's changing in time, the frequency of that external interference. So by that, then we defined roughly at what frequency, which frequency span or frequency range that external interference is hopping or is changing. And that's where we just look for a peak power within that frequency range. So again, these are just the 3 main categories. All of them can be intermittent. That's just from a time domain perspective, but just from a frequency domain perspective, these are the 3 main categories: wideband, narrowband, and frequency hopping. Okay, so In terms of a time domain aspect, sometimes those interferences can be intermittent, meaning that they're not there all the time. So the best way to analyze for those intermittent interferences is basically to log the spectrum. So we can leave a device there just to assess, okay, so probably we know roughly from the management system that this interference happens between, I don't know, say 9 in the morning to 11 in the morning. But we don't know exactly how it behaves. So this is where we log the interference. So we basically leave the instrument and save that spectrum. And by spectrum, that can be based on our PIM detection or RF recipe, or it can be by real-time persistence spectrum or swept-to spectrum. So any of those options which we have available, we can record them and we can process the data. Now, how can we process data? Well, we process data with a free application that we have that is called OneViewer. So this is OneViewer. It's going to give us that flexibility of analyzing the spectrum that we have logged. So this is just an example. Actually, I'm going to be giving you a quick demo on it, just for you to have a sense on how it behaves. While I do that and switch screens here, don't know if there's any questions.
I'm reading through the ones. We don't really have any questions that we haven't answered already. So okay. I think we're good to go.
Very good. Thank you. So this is just a spectrum that we got. This is just an example. Again, this happens to be a 5G TV C-band. So this is just my signal. I'm going to go through some of the settings. For example, I can just play what I have recorded. And as you can see, that's my signal. But now, what if in a post-processing scenario, I want to understand a little bit better and how it behaves in terms of max, average, and min hold. So I can just enable those additional traces so I have a sense of the behavior of the signal across time. So you see, okay, so there's something happening. I have this hump that I see. Actually, that's most likely is my SSB. Let me just do a further analysis on that hump. So I'm going to be using markers, and I can, as you can see, I can allocate different markers. Say, okay, so it's probably going from here, and then I can make another marker to here. So again, even if this is just the SSB being transmitted, but if I see something strange or perhaps an external interference, this is the way to understand or to do the post-processing to see, okay, how is that interference profile, how it behaves, at what frequency is being transmitted, and so on and so forth. Now, the other thing that I can do is, okay, so what happens if I have something that it's just above my limit on my threshold of my uplink, and I want to know when that happened. And let's make the assumption that I just don't want to do this post-processing for that, I don't know, that hour, 2 hours, just staring at the spectrum and how it's jumping up and down to assess for the interferer. So I can actually create a mask, a spectrum mask. So I'm going to create a mask. As you can see, I have my line there. And then I'm going to say, well, I'm going to edit my mask, and then I'm going to say, okay, this is acceptable, but up here, I'm going to put a limit that goes from there to there, and then I'm going to go down here. So this is what is going to be acceptable. This is my maximum. And every instance that the signal goes up, I want to assess for that. So as you can see here down below, I'm just going to pause for a second. I have these blue indexes or blue flags. those are the instances where the signal actually went up my limit. So again, very useful. Imagine that again, we're looking into my uplink and I have a limit and I want just to see the times in which that signal went beyond the limit that I defined. So it's right there. Now, how can I go into these multiple events? So I happen to have here in this example, 23 of those events that went beyond my threshold. So I can just go into these events, say, okay, this is one, this is another one, and so on and so forth. So very easily, I can do a post-processing of my signal by defining my spectrum mask. So I don't have to then go through the entire time that I logged to analyze for the interference. Now, some of the other views that I can get from a post-processing perspective, I can get different views. I can get my 3D canvas just to see how the signal behaves. I can also look for my spectrogram, and I pause, but I can just play it. So again, everything is running. I can also have my view on persistent spectrum. And also I can have my view on the behavior of those markers that I have put on, that I have defined. So again, I have here the power variation of all the markers that I've defined through time. So again, very, very convenient, very easy to use and post-process a signal to assess for intermittent interferences. Okay, so let me just go back into my presentation. And then I'm going to be talking briefly about, okay, so we kind of understand what we need to do with 5GT, the external interference, and how we can analyze the signal and obtain the behavior of the interference by doing a post-processing if needed, just to find, okay, in which category, which group, then we need to track for that external interference between my channel power, RSSI, or peak power. Right, okay, so I know that already. So that then the next step will be to find or locate or hunt for that interference. There are a couple of ways that we can do it. First is what we call a spectrum clearance. So nothing should be transmitting before the radio goes up live. So we can basically look for that spectrum. Everything should be quiet, and we can drive on that area where the radio is going to be serving. Now, if something happens, meaning that if we have a signal that goes beyond a limit that we define, let's say we define neg 100 dBm as my limit, that everything should be below that power level. If anything goes beyond that, then we basically here indicate the power level and put a red circle indicating that we had a problem, we had an alarm. And then we can even analyze the type of signal to look for those external interferences that we observed in our drive test. So this is one methodology. We call it spectrum clearance because this happens to be before the radio is live. Okay, now what happens if the radio is live and we have traffic? So that's our interference hunting methodology. And here we're going to be doing a drive test. We look into the spectrum. In the spectrum, we have already defined the type of interference that we're going to be tracking. And that interference, or the track of the interference, is what we basically is the heat map that we're presenting right here. Based on the power level of that interferer is the color that we're painting this heat map. So if it's red, basically that means that the interferer is coming stronger on that specific location. And then as we drive, we get a circle indicating us that, yep, the system automatically found the interference on that area. and at the end is gonna giving us driving directions to go back into the area that we got more instances with high power level of the interferer. With that, I'm going to shift gears to Dan. If Dan, can you help us with a quick demo of interference hunting with interference advisor?
I would, but I'm getting an error message says I cannot start. Let me try that again. Here we go. Let me know when you can see my screen.
We can. Yep.
I don't know how to get that stuff off the top. So a couple questions came in, asking if we're going to define FDD interference versus TDD interference. I'll attempt to do that now. And we talked a lot about TDD interference only because it's coming, right? It's new. It's C-band. It's band 41. Anything above basically 2.4 Wi-Fi is TDD in the US. So we talk about that because it's hard, right? It's no longer FDD interference where, hey, just tune to your uplink. We've got maybe a PRB analyzer or some tool in our system that points to a specific frequency. So from this point forward, what we're going to chat about here is covers both, right? So the application that I'm going to show is the location finding of an interferer. Mine is set up for FDD right now, but as I go at the end of this, I'll show you the tool. You select as a user, hey, am I doing TDD or FDD? And then the settings change obviously to something that is a gated sweep type measurement. In this case, it will not be gated sweep because of my measurement here. So what I've done is I've connected a what we call the Eagle Eye Tablet Edition. That's the system you're seeing on my screen through TeamViewer. Just want to warn people, TeamViewer and me are not friends. So every once in a while, the TeamViewer system will slow down, and I'll just have to pause and wait for it to catch up. It's wonderful technology. And I'm sitting here on a map in an area, and I'm going to fake some GPS so you guys can see what the drive looks like, right? But just a little bit about what the tool looks like. In this case, I have set this up to keep it fair to everyone. I'm using 900 megahertz as my uplink because I don't want to pick on any one service provider and throw a bunch of stuff in their uplink because I am going to generate an interfering tone through a setup I have here. So I'm picking just 902 will be the frequency, just to be fair to everyone, right? That's not fair to any one provider. As Eduardo talked about, the system is designed to look at a massive amount of spectrum for us, the end user, but the system, when it's trying to make its calculations to help you isolate and geolocate an interferer, we're going to isolate that down to a given area. Some people call them PRBs. I do, right? It's the uplink slots that I get to play with, right? And in the world of LTE, which is what we're talking mostly here in FDD, each one of those resource blocks or those width of the spectrum is roughly 180 kilohertz wide. Actually, I think it's exactly 180 kilohertz wide now that I think about it, for your PRBs, and there are so many of them. So, say there's a AT&T, Verizon, T-Mobile, they tell the end user, hey, it's PRB 33 or PRB 14. We tune to that one, and then we adjust the width to whatever we want, right? I'm using 200 kilohertz, and I'm generating a CW right there. So I've already tuned it to what the operator told me it is, and I don't see it. And that's it. So there's my settings. You can read at the bottom what it is. I'll go back to the map because that's it. Bear with me as I turn on the fake GPS on a little drive route I wrote. Did I get the on button? Of course, I probably missed it. I did. I did that so fast, I didn't hit the play button. Play button. There we go. Now you'll start to see GPS move. Obviously, you wouldn't do this in the real world. You would actually just run the tool. And we're just
interference finding started. Do not attempt to adjust this app while driving.
So as it's driving, so the system is collecting data only where that marker is. And if you want to see where that is a little bigger, it's over here. And I'll start turning up my interferer so you can start to see it grow on the screen there. You'll see that the marker now is holding. I'll go down a little bit so she won't talk to me too much. We collect that data. We put it on the screen. We allow the user to look at it, obviously collect it with colors. As I crank up on the power, once we cross a threshold, hopefully you can hear the extremely loud system in my ear, but maybe not over the phone. It collects this data in multiple ways, right? I'll just give it a second. Now let me turn it back down just so it's a little quieter. So what happens is we collect it, we catalog it, we also strip chart it out. So as you're driving, assuming you're a one-person show, audio is your clue. You're able to look over to say, okay, I've just driven out of the area. In real life, you would probably turn around and drive back, but this is a predefined system, so I can't do that. And the system will continue to collect data. After a certain amount of sample points, and that is on average roughly 10 minutes, it will draw that circle that Eduardo showed in a previous slide, dictating to you, hey, interference is in this area, go drive that route again. Again, I'm pre-driving this in a simulated environment, so obviously I can't do that. But it's quite simple, right? You set it up, you've got your measurement. For those people like me who like to look at the RF and don't really care about the map, I tend to leave this screen open. Map is still working in the background, and now I can, crank on my signal and see what's happening, right? As I move up and down, as I get closer and farther, it's just a history screen of this. Anyone who's done drive tests is familiar with the old snail trails. We just do it a little different, adding some algorithms to the background. One of my favorite features is I'm gonna have this thing pause. You would stop the car, say, okay, I've been driving. I don't have the ability to look at this, but now I can actually go back in time and I can go, okay, where was I? Here, as I get to here, that's what my signal looked like. Here was my location. I'm going to reverse this screen because it's much easier when you see the information we give you. And again, I'm going to apologize about my GPS still moving because that's the simulator. But it allows us to go back in time and look at it while the system's paused, verify where I am. All right, now I can change course. I can uncheck this, go back to my driving, and it will continue. Right?
This app while driving.
In your case, you would not have this gap, but it allows us to see it quickly. And since interference is dynamic in a lot of cases, we give you the ability to take a quick snapshot as fast as possible. We'll take a screenshot, allowing you to go into here, over here, because we hide it. Yep, screenshot. And why that's important is maybe we see something. All right, well, let's go look at Google Maps, right? Now we can see driving through some residential neighborhood. It allows us to do a lot of data while still using the engine in the background. This is a heads-up display that allows us to have massive amounts of control, massive amounts of history, as well as producing reports. So let's assume I'm done. I'll come here and hit stop. It's going to ask me, are you sure you want to stop? I'll say, yeah, I'm going to even save the data, give it a name, so on and so on. I don't need to bore you guys with all of this stuff and my weird keyboard in this tablet, but that's because it's new. I haven't played with it. And we can then go and produce a report, right? I won't fill out the full report, but you give it the chance to go in here, give it a name. You can load all the different images you put in there, add remarks, and it will create a PDF report at the end of whatever we tell it to do. So it's quite a simplistic system set up to work while you're in the car. I'll cancel out of here, so I don't want to do that. And of course, as with everything we do, since you've saved it, there's always a history screen. You can go back in and then say, all right, let's go. Somebody did telegraph path. I don't know where that is. So we're going to go look at the history of whoever had this system before I did, and this was their drive. So it's a very quick way to see overall solutions, go back, analyze, see the data, figure out where the interference is, and move around. You can see in this case, they drove on the freeway looking for it. So.
Very good. Thank you, Dan.
Okay. One question just came in. I'll do this one live. Broadband interfere. Not much to show on the map. The only difference would be from a setup standpoint. Let me get this thing to go. Sorry about the team viewer delay. The only difference between a broadband and a non-broadband for us is this tracking mode you see down here in the bottom. So I'll change the tracking mode to channel power, and then I'm going to change the bandwidth to something like 5 megahertz wide. And you'll see now I can track not only what the marker's doing, but it will track a width of power, so a channel power measurement over the width that I tell it, versus a peak power will monitor the strongest power level in the area I give it. So this would be our narrowband interferer. This is how we would do a channel power. And I just picked 5. We could pick, 10, 15, whatever we want to pick, right? I don't do it by frequency. I'm in the wrong area. That was my fault. I would do it under bandwidth, right? So yeah, so that's how we would track channel power. Everything else stays exactly the same.
Very good. Thank you, Dan.
No problem, Eduardo. I will give it back.
Okay, so let me just go back to the presentation. So next, so we have found the location now. Now that we have found the location, is a matter of finding the source. So what is that device that it's generating that interference? So for that, we then need to do a little bit of a walk test with a directional antenna. And typically we just look for that type of interference. We put a marker, and then we just enable a sound indicator. So similarly to what Dan did with the interference advisor, we have a limit, and every time that interference exceeded that limit, generated a sound. This is something similar. The only difference here is that based on the power level of the interferer, the tone is going to change, meaning that I'm going to have different tones based on the signal strength of my interferer, and that's going to help me to find that external interference. And with that, just going to give you a couple of references and open up if you have any more questions. But I want to thank you all for these kind of best practices sequence and process that we have seen and implemented for external interference.
Eduardo, we've got a couple questions that came in. Figure we'll answer these live since I can't type fast enough. In the ONA 800, we really need a Wi-Fi connection. That is alluding to the interference advisor for those who didn't catch that. In the beginning, that was correct. Now, with the tablet addition to the One Advisor or CA5G, it can be a hotspot Wi-Fi, or it can be a direct USB connection. And with newer tablets, you could even do 2 static IPs through an Ethernet cable with an adapter. So you don't need Wi-Fi anymore. And in the newer platforms, we've given customers the ability to download offline maps. So open streets and trips, or whatever they call it, open streets for offline access. So no longer needed, right?
Yep.
Ron Hall had a great comment. Thank you, Ron. But they used the box during the NFL draft. He said it was not a time saver. So I appreciate that. Walter asked a question, what about interference density versus frequency? And I don't know how to answer that one off the top of my head, Eduardo.
Interference density versus frequency?
Yes.
Huh.
I know. So Walter, I'm not sure exactly how to answer that one. So I'm gonna throw my hands up and say I don't know. Yes, we will this will be recorded. This is recorded, and the PDF will be shared with everyone on the call. Yeah. Except maybe Brad. I don't know if I'll share it with Brad. All right. For example, if we're doing interference something in 700 megahertz, we can set our Wi-Fi to 1900. Correct. Okay, so the comment is absolutely correct. If you are going to use Wi-Fi in our tablet edition, we highly recommend you band lock the phone to a different block band. If you're hunting band 13 or band 17 or band 12 or band 14, I guess, in the 700 block, you would want your phone locked to AWS or PCS, or the 600 if you're using that carrier, to keep your uplink out of the uplink you're interfering for. Yes, absolutely. Great comment. And a whole lot of questions are coming in. So I'll just keep going if you're okay with that, Eduardo.
Yeah.
Is the interference hunter you are showing different from the older version? Well, that's a good question, Sam. The tablet edition has evolved, yes. The underlying engine between the old 785, the CA5G, and the One Advisor were all using the same screen. So it hasn't changed too much from an engine point of view, with one exception. That's the FDD exception, right? FDD, it has not changed at all. For TDD, and unfortunately, I'm not sharing my screen anymore. To do the flexible gate, you do have to use either the One Advisor or the CA5G. We did not support that feature in the 785 for the TDD testing. That is different from the older one. But the tablet is, other than a couple bells and whistles, has been the same since version 1. Yeah. Okay, I believe that's, oh, here we go. Can I get more information about the setup? One Advisor, absolutely. Amandeep, if you could, oh, I hate to have you put your email in there because then everyone's going to get it. I'll put my email there. Let me send you my email. Send me a quick note and I will send you our guides on all of this. Absolutely. Not a problem. We have a question on polarization of the antenna handle. Eduardo, do you want to do this? It's actually, what's the preferred polarization of the antenna handle when looking for interference? I'm going to add that to the end of it.
Yeah, and that actually depends on the environment, but typically when we're looking for interferences, if we do it kind of a vertical polarization, that's probably going to be a little bit better. So typically the way that I do it, I start with a horizontal polarization and then I kind of move it into a vertical, and that's typically, it's going to give me a good assessment on where that interference is coming from.
That's it for the questions so far. We are good to go at this point.
Great, thank you all. I want to thank everybody for joining us today in this third and final session of the Best Practices series for managing uplink interference. As I mentioned, and I did put it in the chat, the links to sessions 1 and 2 on PIM and midband intercell interference are already on our website in the on-demand section. You'll see them with the naming convention that we've used on this event. This event was recorded. It will be available on our website in a few days. Everyone who has attended will get an email with a link to the presentation deck. And once the session is live, I would look for it on our website in a couple of days. I saw one request for us to send it the link to direct. I will try to remember to do that. So want to thank you again. I want to thank our speakers, Eduardo Inzunza today and Dan Smeja, and forgive me for forgetting Steve Dale, who also assisted in answering questions online. So thank you very much for your engagement. We hope you have a great day, and thanks for attending this series.